Okay, our goal in this video will be to factor matrices. Again, factoring matrices. So a matrix A will be factored into another matrix X, L, and X inverse. Actually, let's change this to D, because that is going to be a diagonal matrix. That means that the entries on the main diagonal are going to have some values. Possibly some of them could be 0, I suppose. But then the um, the entries above it and below it are going to be 0. So this diagonal matrix will be of the form um, a some number 1, number 2, number 3 on the main diagonal, and then 0. So this is an example of a 3 by 3. But if we had a 4 by 4, it will be the same kind of deal, where we have a 0, 0 on the two extremes, and then in the main diagonal, some numbers. And this matrix has to be invertible because we got to be able to multiply on the other side by the inverse. So that is the main thing. There's some consequences of this. And the other thing that is going to be important about factoring of a matrix into this format is that we will be able to do powers of A. That's going to be an application we're going to do in this video. But the other thing I wanted to mention is that the entries of the diagonal matrix are actually the eigenvalues of A. And the columns of X are going to be the eigenvectors of A. Essentially, I already told you how to do this. So the diagonal matrix will be made up by the eigenvalues of the matrix A, while X, the columns of X, are going to be the eigenvectors of A. All right, let's start working out one example. So let's say we have the matrix A equals 1, 1, 3, -1. There we go. And we want to factor that into this setup. So first, we need to find the eigenvalues of this matrix. So we do the determinant of A minus the identity times lambda. So that is the determinant of 1 minus lambda 1, 3, -1 minus lambda. So this is a little bit of a review of what we did in one of the last videos when we did the when we found the eigenvalues. So multiply those two. That is really lambda minus 1, lambda minus 1. If we multiply this by -1 and this by -1, when we multiply those two together, we end up with the same product. And that is lambda plus 1. And then minus 3 times 1. So that is lambda squared minus 1 minus 3. And that is, of course, lambda minus 4, lambda squared minus 4, which is lambda minus 2, and then lambda plus 2. So we have two eigenvalues, lambda 1, which we can label as, well, the first one we can label as lambda 1, and the second one we can label as lambda 2, will be -2. Each one of those eigenvalues will have an eigenvector. Let's find the eigenvector for 2. So we want to find, okay, 1, 1, 3, -1. We want to find vectors A, B so that we end up with 2AB, 2A and 2B. So when we move this to the other side of the equation, this 2A to the other side of the equation, we're going to subtract 2 from 1. So we end up with -1. There's no subtraction of this 1 because that affects the B when we multiply. And then 3 stays as is. And 2 gets subtracted from -1. So we have -3. And we can already tell we can if we row reduce, by the way, this is AB equals 0, 0. What I did is essentially subtract this matrix from this matrix. Um, let me elaborate on that a little more. This matrix is the same thing as 1, 0, 0, 1 times 2 A. Yeah, because this is a 4 by 4. Let me think about that for a moment. 2A and 2B. Yeah, so we're subtracting the 2A, yep, from this element, or the, yeah, which actually, let me elaborate a little more. Yeah, this is equal to 2002. That's better. A, B. Yeah. So we want to match the A and B. There we go. So when we subtract on both sides of the equation the 2002, that's how we end up with this matrix, and we end up with 0, 0 on this side. So this is the algebra that is going on. Yeah. If we row reduce this matrix, because we have zeros, the zeros are not going to be affected, and we can clearly get rid of this guy, by subtracting 3 times this guy, or adding 3 times of this onto that. So the bottom line is that we end up with -A plus B equal to 0. Actually, we should go through that step. So I'm going to subtract, and we're going to end up with -1, 1, 0, 0. From here to here, what we did is we added actually R2 plus 3 times R1, AB. And doing that on this side of the equation doesn't affect anything because we got a bunch of zeros anyhow. So 0 plus 0 is 0. And then we can multiply by -1 this row, just to make it a nice row echelon, put this into row echelon form. So R1 times -1 gives us 1, -1, 0, 0, A, B equals 0, 0. All right, so that's where we get either, well, we have a free column, which means B, which is the column corresponding to the B. So B is a free variable. And we have that A minus B is equal to 0, which means A is equal to B. And all we need is one vector. We don't have to have all of the vectors when we are doing eigenvectors. So one easy vector is if we set B equal to 1, so A is equal to 1. So lambda 1 rather equals 2 has the eigenvector 1, 1. And we can verify that if we have if we multiply the matrix 1, 1, 3, -1 by 1, 1, we end up with 1 plus 1, 2, and then 3 minus 1, 2. So it works. We end up with twice as much as this. So the eigenvalue of 2 applies to this vector. So we have one set, one eigenvalue and one vector. Similarly, we find the second eigenvalue. Okay, so, well, no, the second eigenvector. So 1, 1, 3, -1 multiplied with AB. So this is a new thing. We're still within the same example, but it is a new eigenvector. Oh, -2A and B. Yeah, because we want this vector to be multiplied with -2 after we multiply by this matrix. And by the way, that is -2, 0, 0, -2, A, B. There we go. And so we can subtract on both sides of the equation this whole product. And then, yeah, let me do that. So we have 1, 1, 3, -1. And then when we subtract, we can factor out AB minus -2, 0, 0, -2, still times AB. Now, when we subtract, we end up with 0, 0. And then we just do the subtraction here. And we end up with 1 minus -2, 3. The 1 is preserved, 3 is preserved, and then -1 minus -2. Wait, let me check this. 1 minus -2 is 3. 1 is okay. 3 is the same. -1 plus 2. Oh, yeah, it is 1. Yeah. So we end up with 0, 0. Yeah. If we row eliminate, if we simplify this by elimination, a simple subtraction, row 2 minus row 1 is going to give us 3, 1, 0, 0. AB equals 0, 0, which means that 3A, we could divide by 3 if we wanted to have it at row echelon form. But what I'm after is the vector, the eigenvector. And so I try to avoid fractions if we can. So we have 3A plus B equals 0, 3A plus B equal to 0, and this one doesn't matter anyhow. So we have a free variable, a free column, B. We can set B to be 1 again. Yeah. If actually, oh, this gets a little tricky. If B is 1, then A has to be -1/3. If B equals 1, then A equals -1/3. But an eigenvalue produces a space where every element in that space, a subspace rather, is an eigenvector. No, I said that wrong. An eigenvalue has an eigenvector for which every multiple of the eigenvector is an eigenvector of the same eigenvalue. Boy. Okay, so we got an eigenvalue, lambda, and then we have an eigenvector, v, corresponding to this lambda. But it turns out that this v, it's just a point somewhere, and then there's the origin. Any point on this line through v and the origin, any point on it, is also an eigenvector corresponding to this lambda. So what I'm trying to say is that the eigenvector is not unique. There's many of them. What is unique is the direction. There's only, yeah. So if b is equal to 1, then we have the eigenvector 1 on the b and -1/3. But if we multiply by -3, just the scalar -3, then we end up with 1, -3. And that is a more pleasant kind of a vector, eigenvector to work with than this one. So we can modify it a little bit to have no fractions. This one has fractions. I prefer no fractions if we can help it, just because the computations are easier. Now let's double check. 1, 1, 3, -1 multiplied with 1, -3 should be -2 times this. But let's double check. 1 minus 3 is -2. 3 plus 3 is 6. So sure enough, if we multiply this by -2, we end up with that vector. So that means that this is an eigenvector with this eigenvalue. Okay, so that is just a review. All of this is a review of a previous video in which we saw eigenvalues and corresponding eigenvectors. Right now we have two eigenvalues, 2 and -2. So we can even make a table. The lambdas are 2, -2. The corresponding vectors, eigenvectors, are, now I forgot which one the other one was. Let me keep this one. 1, -3, 1, -3. And the other eigenvector is 1, 1. Yeah, it is 1, 1. We're pretty much done with this. It turns out that we can, well, let's form the diagonal matrix. The diagonal matrix will be -2, rather +2, 0, 0, -2. The X matrix will be formed by those eigenvectors. Make sure they're in the same order. So first the 2, and then the -2. That's the vector that corresponds to 2. So that goes first, 1, 1, 1, -3, 1, -3. And then we need to find the inverse. The inverse, this is an easy one to do, I think. So switch those two elements, -3, 1, and then put negatives on the other. Is that the inverse? Let's see. If we multiply, we end up with -3. -3 minus 1 is -4. Okay, let's keep that in mind. On the other diagonal element, we got -1 minus 3, that's -4. So those two are consistent when we multiply. And then if we do this column and this row, we get 0. And then this row and this column gives us -3 plus 3 is 0. So it looks like we need to multiply by 1/4. So this is not times 1/4. Actually, -1/4. Let me start all over. X inverse equals -3/4, 1/4, -1/4, and -1/4. And now we do have the inverse function. So this inverse function, this not inverse function, inverse matrix of X. And again, let me double check. -3/4. -3/4 minus 1/4. That doesn't give us +1. We are supposed to end up with 1. Let's see if this is consistent with this product, this row with this column, -1/4 minus 3/4. That is -1. And then if we multiply those two, boy, -3/4 plus 3/4 is 0. So it looks like we need to multiply by -1, and then we will be okay. Boy, it's a good thing that I was checking. And let's check one more time. 3/4 plus 1/4 is 1. The other diagonal element, 1/4 plus 3/4 is 1. And then double check this product, 1/4 minus 1/4 is 0. And then 3/4 minus 3/4. Yeah, so this is the inverse. So the claim is this. The original matrix A is equal to X d X inverse. A is the original A we started out with is 1, 1, 3, -1, 1, 1, 3, -1. X is 1, 1, 1, -3, 1, 1, 1, -3. The diagonal matrix is 2, -2 in the main diagonal, and then zeros everywhere else. And then the inverse is this one with the fractions, -2 no, rather positive 3 over 4, 1 over 4 across, 1 over 4 again down here, and negative 1 over 4. Whoa. Okay, so we have successfully um, factored A into 3 matrices, a matrix which is the matrix corresponding to the eigen um, vectors. So those are the eigenvectors corresponding to these eigenvalues. And that gives us this and then we're multiplying with this inverse, we have the complete factorization. Yeah, we cannot really talk too much about the inverse, rather the eigenvectors in this context. The eigenvectors show up here, but they don't show up there. All right, so here is the factoring. One of the things I'm going to be asking you in assessments will be to factor, and this is the factoring we want to end up with. So if I ask for the factoring, the diagonal factorization, and this setup, this is what we want. There is an application to this, but we're going to make an example out of this. Okay. So here's the application to this. Let's label this as example 2, which is a follow-up of example 1. Okay. A is going to be the same matrix we started out in example 1, 1, 1, 1, 1, 3, negative 1. Okay, and here's the problem. We want to find a to a fairly large number. I'm going to think a fairly large number. Let's say 40 times 12, 7. Okay, times the column vector 12, 7. So here's what we want to do using the factoring of the matrix A. Okay, so what does this really mean? Okay, so let's understand what the problem is. So we want to do 1, 1, 3, negative 1 times 1, 1, 3, negative 1 times 1, 1, 3, negative 1. 40 of those, 1, 1, 3, negative 1, multiplied, so 40 of them, and then multiply with 12, 7. So we got to multiply this out and this out. There's a multiplication of matrices is associative, so we could even start multiplying those two, and then attaching another one and multiplying again. So for instance, let me just start out with a couple of them. So 1, 1, 3, negative 1 times 12, 7. Let's see how much that is. Well, that is 12 and 7, 19. And then 36 minus 7, that's 29. Okay, so if we did only 1A times 12, 7, we end up with this. Now, so that is equal to A times 12, 7. If we multiply this answer, 1929, by 1, 1, 3, negative 1 again, we end up with, let's see, 19 and 29, that is 38, 48. 48, 9 and 9 is 18, we carry, yes. And then 3 of those, which is 57, minus 29, let me double check with this little calculator. 57 minus 29 is 28. 28. So that would be a squared of 12, 7. And then if we did one, let's do one more. So if we take this answer rather, and multiply it with 1, 1, 3, negative 1, so 48 times, and 29, 28 rather. Anyway, so that's, we are going to add those two, and that's going to give us 16, carry 1, 76, and then 3 48s. 3 times 48 equals 144, and then take away 28 minus 28, that gives us 116. So that is a cubed times 12, 7. Because every time in this interaction, we're going to start multiplying with a, and then the answer multiplied with a again, and then the answer multiplied with a again. So by the time we get to this point, we have a cubed. I just want to double check this 28. So that is 3 times 57 minus 29. Yeah, that looks right. Okay. So the question is, if we kept doing this for a while, what would be, I mean, eventually we will get to a to the 40 of, or times 12, 7. Yeah, that's, 37 more steps. We could do it by hand. I don't know, to be honest, I didn't even try to check with a big calculator how to do this, but the point is not to do it with a big calculator, with software, with technology. What we want to do is be able to figure this out by eigenvalues, by hand, essentially. Okay. So this is what we're going to do. We're going to take the 12, 7, which is the one where the starting point, and we're going to try to find a linear combination of 12, 7 using the eigenvectors. So this is equal to C1, 1, 1 plus C2. What was the other eigenvector? So I'm going to come back to the end of example 1. There it is. So the eigenvectors are 1, 1, and 1, negative 3. 1, negative 3. There we go. And we want to find a linear combination of those. Okay. So 12 is equal to C1 plus C2. And 7 is equal to C1 minus 3 times C2. And we can subtract one equation from the other. So 12 minus 7 is 5. And that's going to be, the C's are going to simplify out. Let me double check this. C1 plus C2 is 12. 7 is C1 minus 3 times C2. Yeah, I guess it is correct. And then we subtract, so 5, C1s will simplify out. C2 plus 3 C2, that's 4 C2 Yep, looks right. So C2 is a fraction. I wasn't anticipating a fraction, but it is what it is. So C2 equals 4 over 5, rather 5 over 4. And C1, 5 over 4, we can solve this equation for C1. So 12 minus C2 is C1. C1 equals 12 minus 5 over 4, and that is 48 over 4 minus 5 over 4, and that is 43 over 4. Okay, so 12/7 is equal to a linear combination, 43 over 4 times 1, 1, plus 5 over 4, 1, negative 3. Okay. Yep. Yep. We're almost there. This is, so remember what we want to do. We want to do 1, 1, 1, negative 3 to the 40 applied to 12/7. Well, but that is the same thing as 1, 1, 1, negative 3 times 43, 4. Yep, 43 over 4 times 1, 1 plus 5 over 4 times 1, negative 3. Okay. Um, We can distribute this multiplication. Oh, this is to the 40. Or the 40 is too large almost. I almost regret doing that large of an exponent, but we will finish it. We will still be finishing. So we will distribute. Now, this is a constant. This is just a constant, and this is a constant. Constants can factor out. So we end up with 43 over 4. 43 over 4. And then we distribute this matrix on here. I'm going to label it as A, if that's okay with you guys. So A times 1, 1. Yep. Oh, A to the 40. Plus, this notation is messed up. Sorry about that. It is 43 over 4, A to the 40. There we go. 1, 1. Plus 5 over 4, A to the 40 applied to 1, negative 3. There we go. Yep, yep. So what we are, this is A without the 40, or A to the 40 if you want to, same thing. So we're distributing over this addition of matrices or vectors, and the constants factor out. So here are the constants factor out of each one on each one of the products. But here's the part that is really, really exciting, I think. This is an eigenvector, and so is this. Those are eigenvectors. And consequently, the eigenvectors, when we multiply the matrix, end up with the eigenvalue multiplied with the eigenvector. See, let's recall something. Okay, so we're going to continue with this equation, but I want to remind you of something. What is A of 1, 1? We already know that. It is 2, 2, because this is an eigenvector and corresponding to the eigenvalue 2. So what it does, it multiplies it by 2. So what is A squared of 1, 1? Well, that is 4, 4, because we're multiplying 1, 1 by 2 twice. Well, if you get 40, 1, 1, then we're going to end up with 2 to the 40. Every time we apply A, we're multiplying 1, 1 by 2. So 2 times 2 times 2 times 2, 40 times. And that's the beauty of working with eigenvalues. Multiplying with a matrix, you don't have to multiply, row and column, 40 times. You can just say, oh, well, it's just going to double, because that is the eigenvalue, the vector, 40 times. Same thing happens with 1, negative 3. A, 1, negative 3 will be negative 2, 6, because we're multiplying by negative 2. So 1 times negative 2 is negative 2. Negative 3 times negative 2 is 6. Or the other way to put it is negative 2 and then negative 3 times negative 2. There we go. a squared of 1 negative 3 will be negative 2 quantity squared, and negative 3 times negative 2 squared. Yeah. So if we have a to the 40, yeah, that's going to be 1 negative 3. Um, let's think about this. Negative 2 to the 40, and the other coordinate will be negative 3, which is the original vector, times negative 2, whoops, to the 40. There. Negative 2 to the 40. By the way, since we have an even exponent, the negatives are going to go away. So this is the same thing as, only because we have an even exponent. If we had an odd exponent, then the negatives don't go away. So we have 2 to the 40, and then negative 3 times 2 to the 40. All right, so now let's go back to this. A, thus, a to the 40 applied to 12/7. 12/7 is, I'm going to copy this again, 43/4 a to the 40 applied to 1/1 plus 5/4 a to the 40 applied to 1 negative 3. All right, but this is the eigenvector corresponding to the eigenvalue 2. So what we have to do is multiply this eigenvector by 2 40 times. So 43/4, and we have 2 to the 40, 2 to the 40. Yep, plus 5/4, same thing here, negative 2 to the 40. Now, I'm going to put 2 to the 40 only because the exponent is even. If we have an even exponent and we are raising negative 2 to an even exponent, the negative goes away because we have an even number of negatives. You know, negative 40 negative ones, essentially. And so every double negatives are going to turn into plus. Here, the negative 3 remains, but then we still multiply it by 2 to the 40. Now, the beauty of this is that we already have an answer. We don't have to multiply by matrices anymore. No matrices. We're done. I mean, we're done multiplying by matrices. Remember, the complication with the original problem was, you multiply by a matrix to get an answer. You multiply by a matrix to get an answer. You multiply by a matrix to get an answer. And this gets really, really long. I mean, we have to do that 40 times if we did that, by actually multiplying the matrices. But if we use the eigenvectors, then this is way, way faster. Let's simplify this into a nice, neat vector. I think we can do that with a little bit of algebra. I'm going to start a new page here. So this equation continues on this page is 43/4, 43/4, 2 to the 40. So I'm multiplying the scalar by the vector, 43/4, 2 to the 40, and might just as well multiply with the scalar and add it on the same vector. So this is a vector, and we're going to add 5/4 2 to the 40 minus, and then we need to multiply 15/4, 15/4. So 5 times 3 is 15/4, 2 to the 40. 2 to the 40. Okay. Well, we can factor out 2 to the 40, and 43 and 5 is 48 over 4 is 12. So we end up with 12. And here we can factor out the 2 to the 40 out, actually. So we have 2 to the 40 factored out. And 43 fourths plus 5 over 4 is 48 over 4, which is 12. 43 minus 15, 38, 28 over 47. Oh, isn't that funny? Yep, yep. So it turns out that if we wanted to multiply, by the matrix 40 times, it is the same thing as multiplying 2 to the 40 times the original vector. That rule will be consistent as long as we have an even exponents. Had we had an odd exponent, then the answer would be different. Then there would be an extra negative here and an extra negative here. And so things will be different. But there it is. There's the answer. There's the beauty of this. We don't have to multiply with the matrix 40 times. Yeah. In fact, it gets to a point after a while where the calculator cannot do 2 to the 40 anymore. Let me just check very quickly. What does the calculator try to do? Let me clear this up. 2 to the 40. Oh, it does give us some kind of big number. So if I was doing this, let's do something big like 100. Oh, 100 does it. What is the biggest 2 that we can do with the calculator? 500. Yeah, that's when we have an error. So I don't know. In an assessment, I will be tempted to do 2 to the 500 because I know the calculator won't be able to handle it, but we will be able to handle it. If this problem had 2 to the 500 instead, can you do it by hand? Sure. All your answer would be 2, 500 as the exponent, and then you're done. So as long as we have an even power, no problem. Yeah. It is very, very nice to be able to do this. Let's do a second matrix, 3. So we're going to do a 3 by 3 matrix. It took me a while to come up with one. But there's the matrix A, 16. So it is a 3 by 3 matrix, 16, 11, negative 41, 13, 26, negative 67, 5, 7, negative 18. It took me a while to come up with a nice matrix. While. Like 2 hours. I made a couple of mistakes along the way. I hope I don't make the same mistakes. But anyway, so let's start with this matrix. What is our initial goal? Our goal is to end up with A equals X diagonal X inverse. So that is our goal, to factor A. And that's why we call this diagonalization, because this matrix is a diagonal matrix. X inverse. What was I going to tell you? Yes, that is our goal. Yeah, to find the diagonal matrix and this matrix, so that when we multiply those 3 together, we end up back with A. But this is the answer. The answer should look like the answer in problem number 1 of today, in example number 1. So here's example number 1. A, this is A, equals X, D, and the inverse. Except that now we have 3, a 3 by 3. All right. Now this diagonal matrix is made up by the eigenvalues of this matrix. So, so we have to find the determinant of the matrix 16 minus lambda, 11, negative 41, 13, 26 minus lambda, negative 67, 5, 7, negative 18 minus lambda. All right. I'm not going to go through every step. It starts here. This is my scrap paper. It starts here. You know, I did 16 minus lambda times this cofactor, you know, and then minus 11 times this cofactor, and then plus negative 41 times this cofactor. Whoops. And so here's the original setup, and then I simplified it into here, simplified it into here, multiplied out. You know, there's some big numbers such as 1599, 1111 that show up. I don't want to necessarily go through all of those steps again. I just want to show you the computations. And we end up with the determinant. I'm going to copy the determinant from my page here, equals negative lambda cubed plus 24 lambda squared minus 191 lambda plus 504. Okay. Now, the way we find the lambdas is to set that equal to 0. So now, mind, I did go through all the computations by hand. You know, this by cofactors. I actually came up with and that is in this at this level, that is the expectation that students are going to go through all of this. We're going to set that equal to 0 to find the lambdas, which means we can multiply everything by -1. So we have lambda cubed minus 24 lambda squared plus 191 lambda minus 504 equal to 0. And we want to start figuring out the roots of that. One way to see if we have a rational root is to break this up into as many factors as we have, such as, well, let's do that. 504, we can split it up into 2, and that gives us 252, which we can split into 2 again. 126, which we can split again into 2, 63. We cannot split that into 2, we can split it into 3, and that gives us 63, 21, which we can split into 3, and that gives us 7. And so all the factors of 504 are 2, 2, 2, 3, 3, 7. Let's see if 7 is a factor or a solution to this polynomial. And this is from college algebra. We can use synthetic division, -24, 191, -504, to see if 7 is a solution. If I give you a problem this large, I might give you one of the eigenvalues as part of the problem so that you don't have to search, because there's many problems that could work and you don't know which one could work. And if you, in this case with a cubic, if you know one solution, that will make it a lot easier to find the other 2 solutions. So I might give you one solution, say 7. 1 times 7 is 7. Let's use synthetic division, that is -17. -17 times 7. I'm going to, I can do that without the calculator. 7 times 7 is 49. We carry 4. 1 times 7 is 7, and 4, 11, but then we have to subtract. And so 11 minus 9 is 2. 8 minus 1 is 7. Okay. And then we multiply by 7. So 7 times 2 is 14. We carry 1. 7 times 7 is 49, and the one we carry is 50. Oh, so we get 0. That means that we do have 7 is one of the eigenvalues, is a solution. So that's a keeper. Furthermore, we can simplify this into lambda minus 7 times lambda squared minus 17 lambda plus 72 equal to 0. See, once you know one solution, you can apply synthetic division. So we can factor the original polynomial into two polynomials. And then by the zero product property, we can say, well, one solution is 7, and this polynomial gives us the other two solutions. We can factor that. And if we cannot factor, we can use the quadratic formula. But I think we can factor this as negative, what two numbers multiply by 72? Let's see, 72 could be 36 times 2, but that doesn't give us that. What else? 36. 18 times 4. Nope, that doesn't give us that. 9 times 8. Yep, 9 times 8. So 8, 9. Okay, so we have three eigenvalues, 7, 8, 9. Lambda 1 is 7, lambda 2 is 8, lambda 3 is 9. Three distinct eigenvalues. This wasn't very creative because they're just 7, 8, 9. All right, so now we want to find the corresponding eigenvectors. By the way, what we have this far is the diagonal matrix 7, 0, 0, 0, 8, 0, 0, 0, 9. The eigenvalues gives you the eigenvalues rather gives you the diagonal matrix. To be found, we still need x and the inverse. But of course, if you know x, then the inverse is easy. Well, easier. You know how to use the Gauss-Jordan elimination method to find the inverse. Okay. So put that on the back burner. Let's figure out the eigenvalues, rather the eigenvectors for 7, 8, and 9 respectively. So the original matrix A, we want to find the vector V so that AV equals 7V. That's the whole point of an eigenvalue. Rather, the eigenvalue is 7 and the eigenvector. Okay. Oh, we need to know A. So how do we go about doing this? A is 16, 11, negative 41, 13, 26, negative 67, 5, 7, negative 18, and we want to find a vector A, B, C that gives us 7A, 7B, 7C. That's the whole point of an eigenvector corresponding to the eigenvalue 7. Okay, but as we did it with the 2 by 2 matrix in example 1, we know we have to take away 7 from 16, 9, and the other two remain the way they are. 7 from 26, 19, and the other two components remain the way they are. 7 from negative 18, negative 25, the other two entries remain the way they are. Now, we're still going to have ABC, but then this is going to be 0, 0, 0. Yeah. And then we want to solve that for A, B, and C. We are going to have, because of the way eigenvectors work, If you double the eigenvector, you double this. If you triple the eigenvector, because the 3 involved in the tripling can be factored out, and the same thing happens here. So what I'm trying to say is we're not going to end up with only one solution. We're going to end up with many solutions, which means we're going to have free variables. What we want to do is simplify this into a row echelon form. Row echelon form. Let me pause for just 1 second. After row reducing this, so I'm going to skip the steps of row reducing. We end up with 1, 0, negative 3 halves, 0, 1, negative 5 halves, and then 0, 0, 0, which means we have a free column. This is almost too reduced because, as I have mentioned before, I'd rather not have a fraction. So I'm going to multiply this row by 2, back by 2, 0, negative 3, 0. Same thing with the second one, negative 5. And then 0, 0, 0. What does that mean? That means that A, or 2A rather, minus 3C is equal to 0, while 2B minus 5C is equal to 0, or 2A equals 3C. And so if C is 1, that's going to mess up the, I still have fractions. I'd rather not have fractions. So maybe C could be 2. And let's write this down. 2A equals, let's put a comma in between, 5C. So I want C to be an even number so that it matches that. So if C is 2, that's 6, and A has to be 3. And if C is 2, A has to be 5. By the way, this is B. Yeah, B. So if C is 2, A has to be 3. If C is 2, B has to be 5. So 3, 5, 2 is an eigenvector. Okay, so we have the eigenvalue 7 with corresponding eigenvector. Now I forgot what it was. Oh, 3, 5, 2. 3, 5, 2. Okay, let me check with what I did. Yeah, that's what I got earlier. Okay. Through the same process, lambda equals 8. Now, mind, please mind, it is a long process. This is the original setup, to find the eigenvector for 7. And then row reduce, and I skipped to show you how to row reduce it. There's a lot of steps involved in row reducing this. And then we got to that. And then we have the equations. And then I pick numbers that are easy to work on, like 2, so that we don't have fractions. And that is okay. So this eigenvalue corresponds with this eigenvector, or the other way around. This eigenvector corresponds to this eigenvalue. And there was a process, a long process to figure out this eigenvalue, this eigenvector rather. Through the same process, we should obtain an eigenvector corresponding, so we can label this as V1, lambda 1, lambda 2, V2. I'm not going to go through the whole process again, even though I did skip some of it. But 1, 3, 1, 3, 1 is an eigenvector. Now, you can easily double check. if you multiply the original matrix A with this vector, you're going to end up with 7 times this vector. The original matrix A, with the big numbers, multiplied with this vector is going to give you 8 times this vector. And then we have the eigenvalue 9 with a corresponding eigenvector 583. 583. Okay, so there is a lot of work involved on this, figuring this out. I don't know, maybe 15 minutes. Mind, this is work, about 15 minutes here. I mean, by the time you carefully and slowly and figure out the eigenvector, just the row reduction can take a while. And then maybe another 15 minutes here. And that doesn't even, well, that probably takes into account mistakes, because you want to double check. We want to multiply the original matrix with this vector to make sure we actually end up with 9 times this vector. All right. So far we have this. A is equal to X, which is going to be made up by those eigenvectors, 3, 5, 2. 3, 5, 2, first column, 1, 3, 1, second column, 5, 8, 3. Times the diagonal matrix, 7, 0, 0, 0, 8, 0, 0, 0, 9. Okay, so I remember our goal. Our goal is to express A as X diagonal X inverse. Here's the diagonal, this is X. We're missing the inverse. We could go through the process of finding the inverse of this matrix, Gauss-Jordan elimination. That's another 15 minutes if you do it carefully and making sure everything works well. I found the inverse to be -1, -2, 7, -1, -2, 7, -1, 1, -1, -1, 1, -1, 1, 1, -4, 1, 1, -4. So the original A, we should probably write the A, even though there's not a lot of room here, just to have a complete matrix. Then this eraser doesn't work. There you go. I want to have a complete matrix notation. The pencil doesn't show too well, I believe, here. So, and then erase and let's just write it out. So what was the original matrix? So we want to write A equals X diagonal inverse. The original matrix is, let me find it. That was a few pages ago. Okay, so A is the one with the 16, the 1, the -41, the 13, 26, -67, 5, 7, -18. That is equal to the matrix with the columns being the eigenvectors. The eigenvectors are 3, 5, 2, 3, 5, 2, 1, 3, 1, 5, 8, 3. And then we're going to multiply. So we're going to multiply with, I'm running out of space here, so I'm going to write down the other two matrices. Diagonal matrix 7, 0, 0, 0, 8, 0, 0, 0, 9 with the eigenvalues. And then this matrix, except that it's got to be the inverse. -1, -2, 7, -1, 1, -1, 1, 1, -4. There. So that is a big part of the problem. Let me double check the inverse. -1, -2, 7. Yep, that is. So we are successful. This is just a long equation with the big matrices in them. So we have A equals X, D, X inverse. If I were you, and this was one of the problems to do in the assessment, you definitely want to double check that this is the correct multiplication. Multiply this out and make sure that is equal to that. And make sure that those two are inverses of each other. And it does work. It does work well. All right, but now there is one other problem we have to address. 4. Yeah. One of the applications of this is that we can multiply this matrix with itself many times with a vector. You know, in example 2 of this video, we had a to the 40. We could have something like that. Let's do a to the 10. Okay, so the question is, evaluate a to the 10 times a column vector. Now I'm going to pick a column vector that is easy. So I'm going to use some scrap paper. I want to show you how I'm going to come up with a vector. Let's say I have random numbers so I'm going to multiply one of the columns here, 3, 5, 2, 3, 5, 2, and then maybe 3, 1, 3, 1, 1, 3, 1, and then 5, 8, 3. Oh, 4 times 5, 8, 3. Okay, so I'm going to do this step by step. So 6, 10, and 4 plus 3, 9, 3 plus 20, 32, 12. And then we just add all the vectors together. We got 9, 29, 19, and 32. That's 51. 9 and 2 is 11. 4, 5, yep. And then 4 and 3 is 7. 19 again. So that, well, 19. Yeah. So the way I would ask you, I wouldn't show you this, but I want in this video to show you this, because then you see what's going on. Okay, so when I make up the problem, I come up with a linear combination of those columns, which are the eigenvectors. And I just pick a random, which is not very random, actually, because once you pick the two, in this case, I just follow a sequence, although I won't necessarily do that in assessments. But there it is, 2, 3, 4. It's just easy numbers to pick at random. And then we come up with this vector. So what I would ask you on an assessment is, find a to the 10 of 29, 51, 19. Okay, so how do we go about doing this? Well, your first job is to figure out the linear combination of those columns that give this, which I won't tell you in advance. That's part of your job, to figure out what they are. So the way we set that up is by saying 29, 51, 19 equals C1, mystery number, 352, plus C2, 131, plus C3 times 583. And then you got to figure out C1, C2, and C3. You got to solve the system of equations. See, that's the thing. You know what they are. They're going to be 2, 3, 4. But you did, in an assessment, you wouldn't know that. I wouldn't tell you that. That's part of the job. So eventually we get to C1 equals 2, C2 equals 3, C3 equals 4. You know, after you find them, you say, oh, well, that kind of makes sense. He just picked 2, 3, 4. Okay. But you're not supposed to know that. You're supposed to figure that out. So this is the problem, the original problem. Set it up. And this is a follow-up, by the way, from problem number 3, or example number 3. Set it up using the columns that are the eigenvectors. Yep. And once you have that, the problem is pretty much very, very straightforward. Okay, so a to the 10 multiplied with 29, 51, 19 is a to the 10 times 2, the first eigenvector, 352, plus 3 times the second eigenvector, 131, plus 4 times 583. I'm just double checking. 583. Yep. 583. Now we can distribute this inside of those, and those are constants. Those are scalars. So the 2 factors out. Let me do it in 2 steps. I want to make sure we know what's going on. So we do A10 multiplied with 2 i's, 352, plus a to the 10, 3 times 131, plus a to the 10, 4, 5, 8, 3. There we go. Scalars may factor out of a long multiplication of matrices. So we have 2, a 10, 3, 5, 2, plus 3, a 10, 1, 3, 1, plus a, 4. I probably need to get a new eraser. Okay, so scratch that. 4, a to the 10, 5, 8, 3. Okay, now here is the magic. This is the eigenvector corresponding to 7. Eigenvector corresponding to 7. So we are supposed to get this times 7, times 7, times 7, times 7, 10 times. So here's where the magic happens. This is sort of magical. 2 times 7 to the 10, 3, 5, 2, plus 3 times. Now, this eigenvector, when applying a to it, we don't get 7. This corresponds to the second eigenvalue, which is 8. So we end up with 8 to the 10, 1, 3, 1, plus 4 times. That corresponds to 9, 9 to the 10, 5, 8, 3. Yep. So the answer is not going to be beautiful. It's not going to be particularly simple. You know, the 2 times the 3 is 6. So we're going to end up with, I'm going to try to do this in 1. So 6 times, oh yeah. So we're going to end up with 6 times 7 to the 10 plus 3 times 8 to the 10 plus 20. 4 times 5 is 20. 9 to the 10. So that is the first entry of the vector. We're going to end up with a vector. And then we do the same thing here. 10 times 7 to the 10 plus 9 times 8 to the 10 plus 32 times 9 to the 10. And then finally 4 times 7 to the 10 plus 3 times 8 to the 10 plus 27. No. 4 times 3 is 12. 12 times 9 to the 10. Voila. So there we have one entry, two entries, three entries. And that's a large number. I have mixed feelings on whether for an assessment, I'm going to ask you a low um, exponent, maybe 4, because then with a low exponent, we can use a simple calculator like this. We can do, certainly 7 times 7 times 7 times 7 one more time, and that gives us a fairly small number. I mean, in the large numbers, that's fairly small, in the thousands. So this is going to be maybe in the 10,000s, maybe in the 10 or 20,000s, maybe in the 30, 40,000s. But that is going to be a number that we can compute if this number was small, such as 4. Perhaps that's something I could do. And that way we end up with nice numbers. 7 to the 10 is I don't know if this calculator will handle it. 7 times, so that's 2, 3, 4, 5, 6, 7, 8, 9, 10. Nope, it has an error, which means we run out of digits. So that is almost too large to handle. So here, I would be tempted to use a smaller number, but with a 2 by 2 matrix, I will be tempted to use a large number instead. We'll see what I can come up with for assessments. Okay, so let me summarize what we did. So we're going to be given matrix A. We got to come up with a matrix D, which is made up by eigenvalues. We got to come up with a matrix X, which is made up by the columns. The columns are eigenvectors corresponding to those eigenvalues. Now, there's a catch. The columns have to be in the same order as the corresponding eigenvalues. So the eigenvectors, vector 1 should correspond to the first entry of the diagonal matrix here. Vector 2, the second one that shows up in the X, has to correspond to the eigenvalue, the second one, and so forth. So we find the eigenvalues first. Well, then you find the eigenvectors second, and then you find the inverse using the Gauss-Jordan elimination. So that would be, because once you have this, then you can figure this out, 3. Okay. And then we're cool. So that's probably going to be one of the problems I'm going to be asking you to do. Once we have that, and you have to show the factoring, very much like we did with example 3. Oh, too far back. I gotta find it. Oh, I see. It's right here. Okay. So there it is. A, X, D, X inverse. A, X, D, X inverse. So this is one solution. Once we have that, a second problem I'm likely to ask is for the same matrix A, to find A times a vector, a little v, a column vector. Oh, no, with a big power. So A to the n, for instance. Yeah, let me rewrite this as A to the n multiplied with V. Okay. Now you can do this the long way, which is multiply a matrix with a, if this is 4 or 5 times, if the matrix is large, that's going to take too long. Or I can ask you to do this 100 times, the other exaggeration. Well, if we did that, then Hmm. We don't want to do this by hand the way it is. So what we want to do is break this V up into components. The components are going to be the eigenvectors. So C1 V1, where this is the first eigenvector, plus C2 V2. Let's say we have 3. If we have 2, then we have 2, but we could have 3. C3 V3. So first, break up. So that's the first thing you want to do. Assuming we already have the answer to that. Yep. Then when we multiply, so I guess the second step would be to, when we multiply, um, we're going to distribute as we have distributed in example 2 and in example 4, but we're going to end up with C1 lambda 1 to the n, because multiplying an eigenvector by the matrix corresponding, or the matrix which has that eigenvector is simply the eigenvalue multiplied by the vector. So V1. Yep. Plus C2 lambda 2 to the n, which is just going to be a scalar, V2 plus C3 lambda 3 to the n V3. And then the last thing to do is to consolidate that into one. So step 3, consolidate into one vector, as opposed to, a linear combination of those vectors. And then we get our answer. Yep. I think this is fruitful and fun. Once you pass the anxiety of working out the matrices, because that can be a little tedious. I have to admit that finding a lot of these things by hand is tedious. I'd rather do it by hand with fairly small problems. So a 3 by 3 is a small problem for this context. A normal problem, I would say, would be something in the range of, I don't know, 100 by 100, a matrix, a really, really super large matrix. For that, of course, we would need technology. But I want to keep things simple, so I want to do matrices that are 2 by 2 or 3 by 3. That's the largest I want to go. Because I believe there is value on going through the computations ourselves, rather than just asking the calculator to figure out inverses and row echelon forms and so forth. If the matrix is small enough, let's just go through them. I'm going to try to keep things reasonably simple, not too simple, but reasonably simple, trying to avoid fractions if we can. Yep. And this is diagonalization. I'm going to stop the video here.